This video is on section 7.3 notes, estimating a population standard deviation. So just like in the previous two sections, we're going to have two different ways of creating our estimates. One is a point estimate or a single value estimate that we can use to estimate this particular parameter, which in this case is the standard deviation. And the other, just like before, is a confidence interval. So the sample standard deviation denoted as S is the best point estimate or single value estimate of the population standard deviation. And the population standard deviation is sigma. So our goal often when we are doing studies is we want to describe the population, whether that be the entire population of the United States or the entire population of Vance Granville or the entire population of a given city. We want to describe a whole population, but it's not always cost effective or time efficient to be able to go and talk to every single person in that population. And so we take a smaller sample, and we hope that when we get the statistics that describe that sample, that those statistics will also be accurate as parameters of the population. That's kind of the goal. So here we're saying that we would take the single value that we get for the standard deviation of the sample and hope that that could represent the population standard deviation and be pretty accurate. It's even more accurate, however, to get a confidence interval because that's a range of values. So still using the sample standard deviation to estimate the population standard deviation, but doing so without a single value, but talking about a range of values. So when we looked in section 7.1, we used a standard normal distribution with the variable z, and that was for the population proportions. In section 7.2, we used a student t distribution with the variable t for population means. So now we're going to use chi-square distributions with the variable chi-square, and that's what this distribution is. So when you approach these problems, I mentioned this before, but it's easiest when you're approaching them as each individual section: homework assignment 7.1, homework 7.2, homework 7.3, homework, because you know all the problems in that section are going to be with the standard normal distribution table. All the problems in the next section are going to be with the t distribution table. All the homework problems in this section are going to be with the chi-square distribution table. However, once we get to the end of the unit, they're all going to be mixed up. So the most important thing for you to look for is to see in the problem, is it talking about a population proportion? Then make sure that you're using the standard normal distribution table. Is it talking about a population mean? Then use the t distribution table. And then for today, is it talking about a population standard deviation? Then you're going to use a chi-square distribution. So here's some information that describes the chi-square distribution. First, the distribution is not symmetric as it was with the standard normal and with the t distribution. It is skewed, and you can see that it is right skewed. So the peak is on the left and it is right skewed. The values of chi-square can be 0 or positive, but not negative. So when we looked at the standard normal distribution and the t distribution, we found that z equals 0 or t equals 0 was in the middle, and then we had positive z values to the right and negative z values to the left, or t values to the right, t values to the left. Here, that's not the case. For chi-square, we have starting at 0, and then all the values are non-negative. They're all positive. And the reason for that is because chi-square comes from standard deviation, where we were summing several numbers, all the data points, which were values that had been squared. And so that's why we call it chi-square, not because this is a variable that has actually been squared, but because it represents numbers that have been squared. We denote a right-tailed critical value, so a critical value that's found over here on the distribution, as chi-square sub r. and a left-tailed critical value as chi-square sub L. So we're going to have critical values that we find over here in the distribution and critical values that we find over here in the distribution. And because our distribution is not symmetric, we're not going to have the same critical values that we had before, just positive and negative, which is what was happening in section 7.1 and 7.3. So it's going to make our values come up a little bit differently, and I'll discuss that in a second. So as the sample gets larger, the chi-square distribution gets closer to the standard normal distribution. And here's just a sample of that. You can see that as our sample size goes from 11 to 21, our degrees of freedom is 10 and 20. That's one less than the sample size. So as the sample size goes from 11 to 21, you can see that the peak is getting shorter. It's getting less extreme or more variation. I have to think about that. But you can see that the peak is moving from the left more towards the center and spreading out a little bit, so it's going to look more like that standard normal distribution. All right. Down here, keep this caution in your head a little bit. So in the previous days, we kind of wrote our formulas like this. We said here, sigma squared, in this case that's variance, or in our case we're going to do just sigma, would be the standard deviation or the variance minus the standard error, the standard deviation or the variance plus the standard error. And that's not going to be the case today, because our error is not going to be the exact same error on the left side and the right side, because we do not have something that's symmetric. So we cannot express our interval as the standard deviation plus or minus the standard error, or the standard deviation plus or minus the margin of error. We can't express it that way. And to be honest, we weren't really expressing it that way anyway, but we just can't write the formula like this. And that's the only thing we were writing that way in the previous notes. So we're going to make sure that when we write it, we either use this interval notation or this inequality notation, and that we just keep in mind that the critical values are actually different on the left side and the right side, so that we're not treating it exactly the same as what we did in 7.2 and 7.1. Okay, so here is the formula for constructing a confidence interval. N-1 is the degree of freedom, S is the standard deviation, and then we have the chi-square on the right, the critical value from the right, and the critical value from the left. The reason that these are on the opposite sides, you know, the right one is showing up on the left side of the interval, the left one is showing up on the right side of the interval, is because the critical value on the right side is a larger number, and when you divide by a larger number, you get a smaller value. And so the smaller value ends up on the left side, the larger value ends up on the right side. And then again, when we interpret our confidence interval, we're still going to be able to write the same sentence that we were writing before. So first, what I would like for you to do is look at your chi-square distribution table. It looks like this. And so on the chi-square distribution table, we have subscripts. So we have chi-squared, subscript 0.995, 0.990, 0.975, subscripts over here, and then you'll notice these subscripts are a lot smaller, 0.100, 0.050. So the subscript represents the shaded area. It says the shaded area is equal to alpha, where chi-squared is chi-squared sub alpha. So the shaded region, and in this case, the subscripts represent shaded areas that are coming from the right side. So that is different than the standard normal distribution table. When we worked with the standard normal distribution table, the table was represented by shaded regions that were coming from the left. So these subscripts represent areas to the right. So if we're looking at these areas right here that are really small, then these are going to be the right tail critical values. So these right here, all of these are going to be chi-squared sub r. These are going to be smaller values over here. Over here, these values are going to be from the left tail, but since the left tail over here measures an area from the right, then the left tail would really be this whole shaded region like this. And so these represent the left tail critical values, so chi square sub L. So to read these, we're going to have a left tail and a right tail critical value. We're always going to have one of each. And we need to know the degrees of freedom, which is just one less than the sample size. Okay, so we're going to do an example of finding the chi-squared values for this example problem. It says a simple random sample of 22 pulse rates is obtained. Construction of a confidence interval for the population standard deviation sigma requires the left and right critical values of chi-square corresponding to a confidence interval of 95% in a sample size n equals 22. So what we want is to find the critical values for the tails if this is 95% or 0.95. So that means that we have 5% or 0.05 for both tails altogether. And so the right tail is 0.025, the left tail is 0.025. So for the right tail, this one, when we find it in the table, we're going to be looking for a degree of freedom that is 21, and we're going to be looking for chi-squared of 0.025. So degree of freedom is 21. Degree of freedom is 21, and chi-squared 0.025. Right here, 35.479. 35.479. Okay, and then for our left tail critical number, we know that this is 0.025, but it's not measured from the left, it's measured from the right. And so from the right, that's going to be 1 minus 0.025 because it's just the complement. So that's 0.975. So this critical value is going to be chi-square 0.975 with the same degree of freedom, 21. 0.975 and 21, that's 10.283. I mixed these up though. This is on the right side. This is on the left side. Okay. So there's our chi-square sub R and our chi-square sub L. The next problem says, listed below is a simple random sample of pulse rates obtained from adult females. So this is referring specifically to this previous example. So this is based on data set 1, body data, in Appendix B in your textbooks. Construct a 95% confidence interval estimate of sigma and interpret the confidence interval. So we're going to go ahead and write down all the variables, just like we have been doing in the previous sections. So we know that sigma is the population standard deviation number of beats per minute, since we're talking about pulse rates, number of beats per minute in pulse rates for all adult females. And then we need to go through and write down the information that we have. So we have that the standard deviation, we're going to have to solve for that. We know that the sample size is 22 and the degree of freedom is 21. We know that chi-squared from the left, or the left tail, is 10.283. Chi-square on the right is 35.479. Okay, so the standard deviation we're going to have to find because this is a set of data and they didn't give it to us. So I'm going to go through and hit the stat button and plug in my list. So stat, on edit, I'm going to press enter, and I'm just going to type in all of these numbers. So 76, 80, 76, 54, 86, 74, 74, 74, 66, 84, 62, 60, 78, 52, 68, 84, 62, 66, 62, 56, 74, 66. And then I'm going to hit stat again and go over to calc and one variable statistics and just press enter. So if I needed more information, I could get it, but I only need the standard deviation, which is this decimal, and then the number of terms I already have was 22. So standard deviation, it's good to write a few decimals down there. I'll write 4, just so that you don't get a rounding error. 9196. Okay, so I'm going to use this as my standard deviation since this is not my final answer. I believe the rounding for standard deviation is 1 decimal. If your data values didn't have any decimal places, then your standard deviation should have 1. However, this is an intermediate number and not the final answer, and so I'm going to go ahead and write some more decimals for my calculations. So sigma is going to have a lower bound of the degree of freedom, 21, times the standard deviation squared, divided by the larger of these two. Because when you divide by the larger one, you're going to get a smaller value. So this is going to be the lower bound. And then the upper bound is going to be the degree of freedom times the standard deviation squared, divided by the smaller number. So I'm going to type in the square root, and I'm going to do alpha y equals, just so I can type this in as a fraction. So 21 times 9.9196 squared divided by 35.479. And then I'm going to do the next one. Normally, we would have had the exact same calculation and we would have been taking a negative sign and changing it to a positive sign. And in this case, we don't have the exact same calculation. We have a larger number and a smaller number since our critical values are 2 different values. All right, so I have 7.6 and 14.2 beats per minute. Okay, and to interpret the confidence interval, I'm going to write my sentence. So I'm going to say, we are 95% confident that the true population standard deviation number of beats per minute and pulse rates for all adult females lies between 7.6 and 14.2 beats per minute. Okay. Here is the next example. So this is from the previous section. Suppose 40 Chips Ahoy cookies are studied and found to have a mean of 23.95 chocolate chips per cookie with a standard deviation of 2.55 chocolate chips. Construct a 90% confidence interval to estimate the standard deviation of all chocolate chips in all such cookies and interpret the confidence interval. So we're using the same context that we did in a previous section, but now we're looking at the standard deviation instead of the population mean. So sigma is the population standard deviation. Number of chocolate chips per cookie. And this is specifically for Chips Ahoy cookies. Okay, so if we look at the information we have, we know that the standard deviation is 2.55 chocolate chips. We know that the sample size was 40, so the degree of freedom is 39. And now we have to find the left critical number and the right critical number for chi-squared. So I'm going to draw a little sketch of the distribution. It just helps my brain. It looks like that. I know that we are doing the 90% confidence interval, so I know this is the middle 90%. I know that the two tails are 10%, and so that means this tail is 5, and this tail is 5 as well. So the right side is going to be chi-squared 0.05. And then the left critical number is going to be 1 minus 0.05, which is 0.95. Chi-square 0.95. Okay, so I can go through and use my chi-square distribution now to find those. So when we do it, when we look for the critical numbers this time, the critical values this time, what we find is that a degree of freedom of 39 is not even available on the table. And if that ever happens, you'll just go as close to that degree of freedom as you can when you look up these values on the table. So 40 is as close as I can get. And then I have chi-square 0.950, so I'm going to go all the way down, 26.509. 26.509. And then chi-square 0.05. 55.758. Okay, so I've got the degree of freedom times the standard deviation squared divided by the bigger critical value and then the degree of freedom times the standard deviation squared divided by the smaller critical value. So I'm going to take the square root. 39 times 2.55 squared over 55.758. So we have 2.1 and 3.1, and these are chocolate chips. Okay, so our interpretation of the confidence interval is that we are 90% confident that the true population standard deviation number of chocolate chips per cookie lies between 2.1 chocolate chips and 3.1 chocolate chips. And that is very low variation. So that means that these chocolate chip cookies are pretty consistent. They consistently have a very similar number of chocolate chips per cookie. So I'm not going to write down that sentence to save time, but that's the sentence you would write. Okay, the last example problem, and I would love for you guys to actually go through and finish this problem, even though you might be comfortable with the process, because the interpretation of this problem is a little bit different than the previous problems. So this one says a container of car antifreeze is supposed to hold 3,785 milliliters of the liquid. Realizing that fluctuations are inevitable, the quality control manager wants to be 99% certain that the standard deviation is less than 30 milliliters. Otherwise, some containers would overflow while others would not have an adequate minimum amount of antifreeze. A random sample of 24 containers is collected and found to have a mean of 3,789 milliliters with a standard deviation of 42.8 milliliters. Construct and interpret an appropriate confidence interval. That's the same as everything else we've been doing. The thing that's different is what should the quality control manager recommend? So that's taking the interpretation a step further. So sigma is the population standard deviation. Number of milliliters of antifreeze per container. The standard deviation is 42.8 milliliters. The sample size was 24, so the degree of freedom is 23. And then we need our chi-square, the left and the right critical numbers. So I'm going to go ahead and draw my distribution. It says 99%. So there's my 99%, which means that I've got 1% for each of these tails, or 0.5% on each side. So if I've got the decimal for 1% divided in half, that's 0.005. So 0.00, oh, that's my point already, 0.005 on the right side, 0.005 on the left side. And on the left side, I'm not going to call that 0.005. I'm going to call that 0.995. Okay, so I'm going to get my chart out, looking for 23 for the degrees of freedom. 0.995 is right here, 9.260. And then 23.005 is right here, 44.181. So I've got the degrees of freedom times the standard deviation squared divided by the larger number. Oops. This is my inequality. There it is. Degrees of freedom, standard deviation squared, smaller number. Okay, so the interpretation of this confidence interval would be, we are 99% confident that the true population standard deviation number of milliliters of antifreeze per container is 30.9 milliliters to 67.5 milliliters. And this is talking about the standard deviation, or how much the kind of average amount in the container deviates from one another. So the quality control manager wanted there to be less deviation or less fluctuation between containers, less than 30 milliliters. What we just found is that we're 99% confident that that deviation is actually between 31 milliliters and 68 milliliters. It deviates a lot more, which means that these containers are inconsistently being filled. That's what that means. So what should the quality control manager recommend? They should probably recommend some other way of filling the containers that is more consistent, because the method that they're currently using to fill the containers is not consistent enough to have that standard deviation less than 30 milliliters. Not near consistent enough. Maybe they need a different process. Somewhere in the process something's going wrong, or they need a different machine do it, but something needs to change, because right now their consistency is not where it should be. So that's the extra question that we were answering there, that goes above and beyond merely interpreting the confidence interval.